In this video, we're going to take a look at rate monotonic scheduling. So let's start with our little processes here. We have basically our P1 and our P2. Now we're not going to use the full kind of tuple, right, that has 4 things in there. We're only going to need 3. We're basically just going to have a deadline over here, right? It's deadline / period. We're basically going to assume they're the same. And then over here, right, this is going to be my time, right? So this is the burst size. So I have process 1, process 2. Now, the idea here with rate monotonic scheduling is that I'm going to assign some sort of a priority to each of these processes. Basically, what I'm going to do is I'm going to prioritize them based on the inverse of their period, right? So basically, things that have a shorter period will have a higher priority. So in that case, right, basically these here, right, one will have basically a higher priority, right, because it has, I'm going to write just an H here for high. P will have a lower one. The reason P1 has a higher priority is because it has a smaller period, right? So we're going to take the inverse of the period. That'll be our priority. And that'll tell us, if I want to run something, right, what do I run next, right? The thing with the highest priority is what I'm going to run next. Okay, so that's going to be our overall scheme here, right? Is that we're going to throw these processes into the system. Whatever has the highest priority, that's what I'll run. And then, right, if there's some sort of an overlap, right? Maybe P2 is running, and then P1 gets a chance to run again. If P1 has a higher priority than P2, we'll actually support preemption, right? So even if P2 isn't quite done yet, because there's a lower priority than P1, P1 is actually allowed to kind of kick it out, right? And it can jump in and it can run instead. So we are supporting preemption here, right? So it's preemption plus priority is how this algorithm works. And we'll look at an example in a minute. Okay, so the other thing we kind of introduced here, or at least the book introduces, and it is kind of a useful idea, is the idea of CPU utilization. So CPU utilization is basically the ratio of your burst time to your actual period, right? So we're saying that the CPU utilization of process I, right, is this, burst time I over period of I. So the first one, right, is something along the lines of, you can see the final results computed over here, right? But the way we'd get that is by doing basically 20 divided by 50, right? Or the other one should be basically 35 divided by 100, right? So we're just dividing their burst times by we're dividing their burst times by the period size, or period length. So this gives us what's called a CPU utilization. Somehow it is the idea of how much work does that process need to do during its interval, right? So if I have a process with burst size 10, an interval, and period 20, well then basically it needs to be active for half of that, right? So as that number goes up, right, as my for example, I could maybe increase. Let's do little examples here, right? So I could do say 10 and 20, right? That basically gives me my 0.5, right, which basically indicates that over that period for that process, it has that burst time t period 20. Over that process's execution time, right, it's basically going to need the CPU, 50% of the time. But then if I do something like this, right, like I say, okay, 15 divided by 20, what I end up getting, right, is 0.75. That's saying, now that process needs more. Now it needs 75% of that period, right? It's going to need 75% of that period in order to actually do its work, right? If I lower it, right, if I go, 5 over 20, all of a sudden you're relaxing it. You're saying, okay, you know what? I only need to be active, 25% of that time, right? It's a ratio. So overall, what it's showing us is, during the period, right, how much is that, how active does that process need to be? And so there's a kind of a general thought somewhere is that basically, if you have multiple processes running at the same time, what we can think about doing is adding up their CPU utilization. Because clearly, right, if I have 2 processes that look like this, right, they look like 15 divided by 20, or if I have that, they both have CPU utilization 0.75. If I add that, I get basically a number more than 1. I get 1.5. What that sort of indicated to me is that I need more CPU to get these things done, or these processes will request more CPU to get their stuff done than we actually have, available, right? So if we only have 1 CPU, but our CPU utilization is 1.5, well then clearly we don't have enough work to go around. We can't schedule these things, right? So there's kind of this initial rule, and we'll refine it in a minute, of basically our CPU utilization must be less than 1, right? That's saying that there is kind of enough time to go around in the interval so that each of the processes that are active, right, can actually do their work, right, and run their stuff. So just keep that in back of your head, right? So that's what we call CPU utilization. And you can see it's here, right, 0.5 and 0.4 for one of these, 0.35 for the other one. That's basically saying, we sum that to 0.75. 0.75 seems like it's something that'll run, right? It's less than 1. Now I say it seems like because there is actually an additional rule we'll talk about in a minute. And even though there's, some cases where you have basically CPU utilization that's, less than 1, there's still a chance it won't run, just because maybe things aren't available when they need to be. But we'll come back to that in a second. So for now, right, everything looks like it'll run, so we can kind of imagine that. For starters, though, let's kind of make the assumption that maybe we weren't using the priority the way we said we were, right? We said initially we were going to prioritize things based on the size of the period, so small period means higher priority. Let's say we didn't do that. Let's say we kind of reordered things a different way. What would happen? Over here, right, you can see basically we have our P2 is our first thing over here, right? That runs, takes 35 units of time. Then we do P1, takes 20 units of time. notice that right away we get into trouble, right? All of a sudden P1 basically that is hitting its deadline, right? So this over here, right, is supposed to be P1's deadline. P1's supposed to be done by then, but really there's all this bit here, right, that's kind of still left undone, right? So we've already failed. So clearly, right, if we pick our priorities poorly, right, if we try to do things with a larger period first, right, we're going to get into trouble. And that should kind of make some intuitive sense, because a larger period basically means more flexibility for when you can schedule something, right? Something with a smaller period has less flexibility, so that's something maybe we want to try to address first. So let's see if we do follow that rule, right? The solid rule of the priority where P1 goes first. So here we have a little diagram at the bottom, right? You can see initially why we have P1 running. It's the highest priority, right, because it has the soonest deadline, right? P1's first deadline is over here. P2's deadline is over here, right? So we can see that P1 has the closest, well, has the smallest period there, right? And we said period slash deadline would be the same thing. And then these, right, basically we're saying is that implies priority, so P1 has priority. So P1 runs, right, and it completes out, and it's 20 units of time, so we're good there. Once P1's done, right, basically we don't have anything else to do with P1, right? P1, we need to basically wait for its period to elapse before we get another instance of P1 to run again, right? The idea here, right, is these are kind of regular things, right? This is a scheduling algorithm expressed over periods. So P2 gets to run, right? P2 is kind of waiting around. P2 gets to run for basically 30 units of time. Notice that I'm not saying 35, I'm saying 30 units of time here. Because what happens is, right, at that, the 50-minute mark, right, or 50-unit mark, right, that's basically P1's period. All of a sudden, P1 needs to go again, and P1 actually has a higher priority than P2, right? Because we said that P1, the priority is based on the period, and so P1, has a higher priority than P2. Once we get that time 50, we have another instance of P1 to run. Well, basically we'll set P2 aside. So P2 gets set aside, and we run P1 instead, right? So P1 gets to run for 20 units of time. It gets to complete out, and then we return to P2, right? P2 had the lower priority. It has only kind of 5 left, and it'll go ahead and go. Okay, so it's a little bit maybe different than what you might expect, just because it allows preemption, right? So we're basically making sure that whatever is that thing that has the highest priority, that'll always be allowed to complete, and then things with lower priority, those kind of come after, and those are basically allowed to complete, after the earlier priority thing, higher priority things are done. Then this kind of continues, right? And you have basically the same process, occur again and again and again. So we have, these two processes, right? This is sort of like 2 periods here, right? Well, 1 period of P2 and 2 periods of P1. But it's like this is kind of 1 unit. This is another unit, right? It basically repeats. And you can actually look at that, right? Basically say, you know what? If I assume that these are all periodic, and I should, then it's always going to work, right? So every kind of 100 units of time, it'll repeat, right? Every 100 units of time, I'll get something that looks like this, right? It looks like this. These are identical. And if I just verify one of them is okay, well, then I know I'm good to go, right? I know that all these things will be able to complete by their deadline / their period. So it should be, so it is actually a pretty nice thing, right? We can do this offline, figure out whether or not these things will work. So there are kind of some general rules here we can maybe think about, right? Basically, right, period is what matters. So here, right, we're somehow saying that, things with things with a smaller period, right, should be, serviced more frequently, right? Because that means that I'll basically, those things, don't have as much flexibility when they want to run, right? So I need to basically take care of them when they show up. Another thing to think about is that having a smaller period also means having a smaller deadline. And actually, maybe it's the deadline that's important, because the deadline is what messes us up, right? Once we go outside that deadline, then there's a trouble. So maybe a side note, right, is that if we were having some sort of algorithm that maybe tracked against the deadline only, that might be useful, right? That might give us something important. All right, so let's just talk a little bit more about the CPU utilization. So over here, I have kind of another batch of processes, right? So I have P1, P2, right? Here, basically what we're saying is that P1, right, has a higher priority because it has a smaller period, right? Period is in front, and then we have time afterwards, or burst time afterwards. And so here, right, I can try scheduling according to the previous algorithm, right? So the previous algorithm basically says, oh, find the priority, the one that has the priority runs first, and then preemption is allowed, right? And basically, as periods are hit, right, and you kind of, say this process has to run again, right? Well, if it has a higher priority, then you make it run. We could do exactly the same thing here. The problem is, right, and if you look at this diagram here, I have my P1 and my P2, right? So P1 runs, right? P2 runs, P1 basically cuts it off, right, because it has a higher priority, right? We saw it in the previous demo. We have, P1 running again, and then P2 runs again, but all of a sudden, P2 actually, doesn't make it to its deadline, right? Its deadline is right here, and instead, right, P2 doesn't, isn't able to complete by that time, right? It has this kind of gap here of, it wasn't able to complete right before that deadline. So this is a little bit bad, right? You can even see, right, that P1 actually doesn't have a deadline, right, until over here. So really, there would have been time to run this, right? But just because of the way the algorithm works, right, we kind of failed at it. So this doesn't work. Now, if we were to go and compute CPU utilization, right, you could actually go and do it for both of them, right? So if you want to, you basically get your, say 50 over 5 plus 35 over 80. I don't really want to reduce my fractions right now, but according to the slides here, my calculation I did on my own previously, right, this is going to be 0.94. Which is interesting because we said before that CPU utilization, right, if it was less than 1, I had a shot at scheduling it. Well, here I'm less than 1, but it still doesn't work. So this is kind of a strange issue, right? And what's coming from is kind of two things. One is kind of nitty-gritty, and one is more kind of conceptual. The first idea, right, is that the CPU utilization doesn't really capture when a process needs time, right? So certain processes are based on basically the burst size, based on their overall period, right? It's like somewhere in there, right? They need time, right? But it's like they need in a certain part of it, right? And there's this amount of flexibility vary, right? So if your burst time is low and your period is high, you have tons of flexibility. If your burst time is high and then your period is also high, right? They're kind of the same. Well, you have less flexibility, and so that flexibility isn't really being captured all too well. We're just kind of an overall ratio is what we're getting. And so usually, right, it doesn't really capture enough. Another thing is that there is kind of technically some time spent doing like context switches, that type of other stuff. Basically, what it is, right, is you could never get quite to 100% efficiency, right? There's always going to be some sort of a lag you do somewhere because we have to have other bookkeeping stuff to do. And so actually, right, if we're running on processors, if we run on basically n processors, what we have to do is use this formula here. And this formula, I don't have a good explanation for you guys right now on how this works. It's kind of on my to-do list to figure out. This formula here, right, what this is doing is it's actually giving us for a number of processes how many, what is the CPU utilization we can target. So if you want, right, you can basically plug in 1 or 2 or 3, whatever CPUs you have in your system, right, and from that you'll be able to compute. This is the CPU utilization you can expect. And what happens, right, is this basically falls off, and I think this falls off, maybe to, I think it's like 0.70, right? So at a certain point, if you have a bunch of CPUs, it's like you're still not going to be able to get more than 70% efficiency, something like that. The number basically is dependent on how many cores you have. So as you increase the number of cores, right, this will change, and you can kind of use it to predict, what is the CPU utilization I should aim for. Obviously, right, over 1 is always bad, but then it's also a little bit earlier as well, right, and that's what this formula will tell you.